In 18.3, we're going to take up ether cleavage. That means breaking the ether bond. We're going to cleave it like if you had a cleaver in the kitchen. So, ethers, as we know, are stable to basic conditions. So this is going to be under acidic conditions, and we're going to see that there are some limitations here. So first, the general reaction. The general reaction for this is if we have an ether we treat it with a strong acid. Now this takes a strong acid, HBr or HI. Under sort of ambient conditions, hydrochloric acid, despite being a strong acid, is not sufficiently strong to produce this reaction. Now, I've drawn these in a specific way. This is a two-step SN2 reaction. We have a protonation. I'll put the mechanism up in just a minute. And then a nucleophilic substitution once we have made a leaving group. And so we produce products here in a specific way. ROH plus R prime with the halogen, be it bromide or iodide. Now, there are a couple of limitations here. First, because the second step is an SN2, nucleophilic substitution reaction, bimolecular example, the halide always ends up at the least substituted carbon. So if we had just a secondary, if we had isopropyl ether here, we treat this with HBr, we're going to get the secondary alcohol plus 1, 2, 3, 4, 5, 2, 3, 4, 5 carbons, and then the bromide on the least substituted carbon. Now I want to give you another example of this because this is often used with aryl ethers. There's the oxygen. We'll just make this methyl for simplicity here. If we treat this with HI, now in this case, we can't do nucleophilic substitution at an sp2 carbon. The alkyl halide can't attack there. We can't do nucleophilic substitution there. So we get the aryl ether, and in this case, methyl iodide. All right, so quickly touch about the mechanism of this. So we take something simple here. The first step is that the ether gets protonated. It's the nucleophile, the acid is the electrophile, or it's the base, and the acid is the acid. This produces a protonated intermediate. So we have converted what was a poor leaving group now into a good leaving group, because you see this is isopropyl alcohol, which we all know that's a nice antiseptic. It's a very stable molecule. So then my iodide can act as the nucleophile in a simple SN2, displace the alkoxide, and that will then produce isopropanol. All right, so that's section 18.3.